Welcome to the Calculus, a collection of micro lectures, video lessons, and sample exercises. After learning the limit for a quotient of a function, let's talk about the limit of a rational function. Now this is closely related to the limit of a quotient of a function because a rational function is also considered as a ratio or a quotient of two other functions. But we separated this so that we could have a first idea on what is the process for the quotient of a function and then for the rational function. Now take note, for the quotient of a function, that is if you already know the quotient of each portions. Let's say if we have here the limit of f of x over g of x as x approaches certain c. The previous limit theorem for the limit of the quotient of a function is that if you already know the limit of f of x as x approaches c, and you also know the limit of g of x as x approaches c, let's say this is L, this is M. In the previous limit theorem, you can just simply take the ratio of L and M because that is if you already have these two values. But for the limit of rational function, the assumption here is we don't know yet what is L and M. In short, the limit of these two here, let me erase this portion here. Okay, so we don't know these two, meaning we don't have, this is not given, this is not given. So the limit of a rational function here is if we are just going to substitute, okay, f of c and g of c immediately. That is if given or provided that g of c is not equal to 0, because this will be undefined, just like another restriction we had in the previous limit theorem. So this is separated with the limit theorem for the quotient of a function because this is with the use of direct substitution. We already emphasized in a preview video before talking about the direct substitution may not necessarily be the exact value for the limit. So we understand that as well. So here we allow direct substitution as long as the value of the g of c is not equal to 0. Okay, because these two are not yet given. Let us have an illustration here. Let's say we have the limit of 4x minus 5 over, let's say, x plus 3 as x approaches to a certain constant, let's say 2. Okay, so we don't know, or we may not proceed, because in the previous limit theorem for the quotient of a function, if this is not yet given, so we need to solve for this first as x approaches to 2 to solve for L, and we need to solve first x plus 3 as x approaches to 2 to solve for M, and we take the ratio of L over M. If M is not 0, this is the limit of this function here. Okay, but we don't need to go with this because this limit theorem for rational function allows us to automatically substitute our c here to our x here, both numerator and denominator, given that our denominator here, okay, is not equal to 0. Let's find out if we substitute that here. 2 plus 3, that's 5. It's not equal to 0. So we can apply this limit theorem, because if this is equal to 0, then we are going to use a specific process, and we will have an example for that later. So let's continue with this and just automatic substitution, because we know that the denominator will not be equal to 0. So this would become 4 times 2 minus 5 over, we have here 2 plus 3. And by the way, using this limit theorem for rational function, we do not anymore look at the product and then the difference and then the sum here. That is very lengthy. So as we talk about limit theorems from one to the other, we are making shorter processes. So this is 2 plus 3. So you have 8 minus 5 over 5. So you will have 3/5. This is now the limit of this given item without even going through the L and M ideas, because this is L. By the way, this is L, this is M, but we don't know the values of that at first. So we just automatically use the substitution. Again, given that g of c is not equal to 0. Let's have another example here. Let's say the limit of, okay, we have x squared plus 2x plus 1 over 2x minus 4 as x approaches to negative 1. Our numerator is a polynomial function. Our denominator is a linear function. We already have the limit theorem for polynomial function and linear function respectively. But this limit theorem allows us to automatically substitute if this is not equal to 0. Let's try. 2 times negative 1 minus 4, that's negative 2 minus 4, negative 6. So this is not equal to 0. So we can just proceed with the direct substitution. So you have negative 1 square plus 2 times negative 1 plus 1. By the way, direct substitution here for our numerator polynomial function. We already have a limit theorem for polynomial function as well. Please take a review of that. Over 2 times negative 1 minus 4. By the way, these limit theorems are provided in such a way that you can come up with a process that it's okay to substitute as step goes by, okay? Because we are just dealing with these types of functions. So the square of 1 is 1 minus, we have here 2, you have here plus 1 over, that's negative 2 minus 6. Our numerator is 0. Sorry, it's not minus 6, it's minus 4. Okay, 4 over negative 6. The result is 0. Is this acceptable? Yes, of course, because this limit theorem only talks about not possible if the denominator is equal to 0. This is just a numerator. Even if it's equal to 0, that's acceptable. And this is the limit for this given function here. So we'll have more examples to this later, especially for the example if our denominator is equal to 0. So what are you waiting for? Subscribe now.